All right, let's return to the game set to introduce some of the counting principles that are in section 9.3. So we have this deck of cards, which we'll consider as a set itself, and we might want to know how many cards are in that deck. So this was one of your homework problems from last week. Well, using the multiplication principle from section 9.2, I can count the number of cards in that set just by knowing how the cards are constructed. Each has a specific color, a number of shapes, a kind of shape, and a shade, and the multiplication principle tells us there'll be 81 cards. I'm going to go through a series of other questions about the game set to introduce some new counting principles. So how many red cards are there? Well, we can think of it in a number of different ways. Easiest is that a third of the cards are red, right? So if we have 81 cards and 1/3 of them are red, then we're going to get 27 cards. A little word of notation here. I'm using the cardinality, the usual cardinality symbol for the cardinality of the set S, but this section also uses n of S to denote the number of elements in the set S. Okay, so if R is the set of red cards, then the cardinality of R should be 27, or in the notation of this chapter, N of R is 27. So very easy question, right? What about how many cards there are that are not red? Again, this is very intuitive. If I know how many cards we have total, which is 81, and I just counted the red ones to be 27, then the number of cards that are not in the R set, so that would be the number in S minus R, is just going to be 81 minus 27, which happens to be N of S, the number of total cards, minus the number of red cards. This is a general counting principle. If you have a set A and a subset B, and you want to know how many things are in A but aren't in B, then you just take the number of things in A minus the number of things in B. Okay, here's another observation about the cards in the set deck. Let's say R is the red cards, G is the green cards, and P is the purple cards. Then from before we understand that NR is the same as NG is the same as NP, right? They're all 27 of each kind of color. We also see that since every single card is one of those three colors, the number of total cards is simply 27 plus 27 plus 27, right? NR plus NG plus NP. Now, the other thing I want to notice set-wise is that the set S is the union of these three subsets, isn't it? I'm going to make another observation about how S is constructed from R, G, and P later, but for right now, let's inspect unions a little bit more. Okay, so for example, how many cards are there in the deck that are in the set Y, which is defined to be the set of all cards that are either red or green? And the or here I'm using is a mathematical or, so I'm talking about either red or green or both, but of course there is no such thing as a red and green card. Anyway, so the number of red or green cards would just be N of R plus N of G, which would be 54, right? And notice that Y is the union of the sets R and G. All right, well, how about now, let's think about the set Z of cards that are either red or diamond. Now here, again, I have to think about that mathematical or. I could have red cards or diamond cards or cards that are both red or diamond. So I want to be careful about how I count this. It may be useful to come and take a look at the actual deck of cards to see how this count differs from the previous example. So I definitely have 27 red cards. You can see them at the top, and then I could see the 27 green cards in the middle, and when I was counting red or green, I just added 27 and 27. But look at the diamond cards. The diamonds are on the far left, and there's definitely 27 diamonds, but the answer to how many cards are either red or diamond isn't 27 plus 27, right? That would be too many cards. So let me look at these two questions carefully and contrast the method of counting them. So there are red cards and there are green cards, and there are no cards that are both. So the red cards and the green cards are a disjoint pair of subsets of the set deck. And it's the same situation up here, isn't it? The red cards, green cards, and purple cards, that forms a grouping of 3 mutually disjoint subsets of the set deck. So when our subsets are disjoint and we want to count a union, we can just add up the cardinalities of each of the individual subsets. But now back down here, the red cards and the diamond cards do not form a pair of disjoint subsets of S. Instead, they overlap. There are some red and diamond cards that I see here in the upper left. So I understand that if I just take the 27 reds plus the 27 diamonds, I've done an overcount of exactly how many red diamonds that there are. So I can just subtract off the red and diamond cards from my count, and that will give me the correct count of number of cards that are either red or diamond, or in other words, the union of the reds and the diamonds. So there happen to be 9 red diamonds, and you can use the multiplication principle to count that. And so that means that the number of cards that are either red or diamond should be 45. 27 plus 27 minus 9. This is a general principle called the inclusion-exclusion rule for 2 sets. So if you've got 2 sets and you want to know how many elements are in the union, then you just add up the cardinality to set separately and subtract the cardinality of the intersection. Okay, we can do something similar for 3 sets, right? So I'm going to pose it as a question about a counting of a subset of the set deck. So how many cards are red or diamond or empty? That is like empty shading. I start by counting the number of cards in each of those individual subsets. So there are 27 reds, 27 diamonds, and 27 cards that are empty shaded, but I have a lot of overlap between these sets. Let me come back to the deck and just get a visual of that. So I've already seen that the red cards and the diamond cards overlap in the upper left, right? Well, let me identify all of the empty shaded cards. You can also see that there are 27 of these as I circle them. And notice that there are some empty cards that are also red. There are some empty cards that are also diamond. There are some empty cards that are diamond but not red, that are red but not diamond, and then there are empty cards that are neither red nor diamond. So there's a really interesting mix of overlap between these 3 sets. So there are definitely 27 reds, there are definitely 27 diamonds, and there are definitely 27 empties as well, all for the same reason. But I need to take, if I just take 27 plus 27 plus 27, I'm definitely going to get an overcount. And when you have 3 sets like this, the overcount is really complicated to keep track of. Actually, this image right here isn't going to be the best way to keep track of the overcount. So I'm going to go back to the Venn diagram here in a second to help, but the idea is that sometimes we have overcounted a certain type of card just twice, and sometimes we have overcounted a type of card 3 times, namely the empty diamond red cards in the far upper left. So actually the Venn diagram is probably the best place to do this now. I've got 3 overlapping sets. I've got R, the red cards, D, the diamond cards, and E, the empty shaded cards. And I've got cards in each of these possible segments of the Venn diagram, right? And so if I just take the 27 plus 27 plus 27, let me show you which cards I am overcounting and how much I am overcounting them. So if I just do the 27, 27, 27, cards in these little segments of the Venn diagram that I'm marking right now are going to be overcounted twice, basically, because they are in exactly 2 of the sets that I am counting. But right there in the center, any card that is a red, diamond, and empty is counted 3 times. So when I do the 27 plus 27 plus 27, I'm going to have to subtract off the segments that were overcounted twice, and then subtract off that 1 segment that is overcounted 3 times. Okay, so I'm going to try and write all of that out. So if I want to count the union of R, D, and E, so what is the number of elements in R union D union E, I start with this kind of rough count, which is NR plus ND plus NE, 27 plus 27 plus 27, and then I'm going to very carefully subtract off the overcounts. I'm going to sort of do the longest computation possible and then reduce it, but it's this first computation that I'm getting directly from the Venn diagram. So what I'm writing out right here is a subtraction of the cards that were counted twice. So if you look at R intersect D, but subtract off E, the very centerpiece, then that is a segment of the Venn diagram that got counted twice. And same with D intersect E, subtract R, that's the segment to the right that was overcounted twice. And then R intersects E minus D. And then I understand that I need to then subtract off 2 times the number of cards that are in the very center intersection, because I have counted those cards a total of 3 times, and I only want to count them once. So I'm going to rewrite some of the terms of this count a little bit differently. So, for example, if you look at R intersect D minus E, that's the same thing as R intersect D minus the R intersect D intersect E. So rewriting each of those terms like that and using the result, the result from above, I can get these counts precisely. So after having rewritten the blue, red, and green sets in terms of differences of sets, I am applying the difference rule to each of those. And each of the individual terms there are easy to compute using the multiplication rule. And so all that's left to do is just a little bit of algebra, actually. I'm just going to gather together like terms in this expression and then do the individual counts again, using the multiplication rule. So what I've actually constructed here is a general way of counting the number of elements that are in a union of 3 sets. It's just the sum of the elements in each of the individual 3 sets, subtract off the intersections of each pair of those sets, and then add back in the intersection of all 3 sets. Okay, so with all of this stuff figured out, let me come back up here to the original question and use this inclusion-exclusion rule together with the appropriate counts and figure out sort of what the answer is. So what I've got is that the number of elements in the union of these 3 sets is written in terms of the number of elements in R, D, E, each of the pairs of intersections, and then the triple intersection. So let me actually figure out what those counts are up here using the multiplication rule. And by the way, the number of elements that are red and diamond is going to be the same count as the number of diamonds and empties, which is going to be the same as the number of red and empties. And that is all 9. And you can think of it in terms of the multiplication rule like the following. Let's say if I'm trying to figure out how many cards are red and diamond. Well, all that's left to decide is what shape are we talking about and what shading are we talking about. And since there's 3 shapes and 3 shadings, that gives you 9 total possibilities for red diamond cards. And it's the same logic for the other 2 intersections. And then finally, the triple intersection, how many cards are red and diamond and empty? Well, that's all that's left to be counted there is the shading, so there are only 3 possibilities. So in the end, I can come back over here and get the count that I wanted. So how many cards are either red or diamond or empty is 27 plus 27 plus 27 minus 9, 9, and 9. So that's another minus 27. And then you add back in 3. So altogether, I have 57 cards. And maybe it's worthwhile going up to the image of the entire deck and seeing that we have exactly 57 cards that satisfy that category. Okay, but of course, importantly, this now is a general rule for computing the number of elements in a union. We've got the number of elements in a union of 2 sets, 3 sets, and it's a great exercise to draw yourself a Venn diagram and figure out a formula for the number of elements in a union of 4 sets. It gets really messy, but I mean, you can do it using the same logic. The last thing I want to say is that now that we can count the number of elements in subsets, you can compute probabilities. Probabilities are just computed from cardinalities, so you'll see the book asks you these same sorts of questions, but they're phrased in terms of probabilities. So like I could take the question that I just worked out and ask a probability question. I could say, suppose I choose a card at random from the deck, what's the probability that it's red, diamond, or empty? Okay, and the answer here is simply the number of cards that satisfies that condition, so the number of red diamond or empties, over the total number of cards. So we have just computed the cardinality of R union D union E to be 57, and that's taken out of 81, and that is about a 70% chance.